My name is Lisa Reusch, and I am really excited to be here giving a talk on Python and the future of fusion energy. And one of the reasons that I'm really excited to be here, and one of the reasons that I'm here giving this talk, is that the last couple of years have been just really exciting for fusion. We've seen record levels of private funding invested into fusion power, and associated with that, there's been a record number of fusion power startups started. These are companies that are specifically devoted to bringing fusion power to the electrical grid. And of course, we've seen some really exciting scientific breakthroughs, including the recent announcement of fusion break-even from the National Ignition Facility. And I'll talk a little bit more about what this means in a few slides. But through the course of this talk, I really hope to convince all of you that we in Fusion have increasing opportunities for experts in data-driven technologies and data-driven solutions. Before I get into the meat of the talk, I just kind of want to give a little bit of a roadmap to where we're going, because this talk is going to cover, we're going to cover a lot of ground in this talk. So I just want to have a little roadmap and some signposting to keep us on track. So I want to start off with a brief introduction to fusion science, and then I'm going to give three specific examples of projects that are being worked on where I think the wider Python community can help, can get involved. And the idea with just going back to the introduction, the idea behind the introduction is to just give you enough science so that you understand these concrete examples. Hopefully I don't go overboard. I am a scientist. I like to geek out a lot. With that, I'll just jump into the introduction. Fundamentally, fusion is a nuclear reaction. It's a reaction where the nuclei of two light atoms bond together and release energy. And so here we've got a little diagram of a fusion reaction. We have two hydrogen nuclei, and the nuclei of atoms are made up of protons, which are the red circles here, and neutrons, the gray circles here. And these two nuclei are isotopes of hydrogen. They're going to slam together, bond, and they form a helium atom nucleus. And then there's this extra neutron that flies off all by itself. In addition to these two particles, the other thing that's released in this reaction is a boatload of energy, just a lot of energy. And it's this extra energy that we want to harvest in a fusion power plant and turn it into electricity. Now, at this point, I want to introduce the idea of break-even and what that is. So it turns out that it takes some amount of input energy to get these two nuclei to fuse in the first place. So we have to put some energy into the system. And the idea is, in a fusion power plant, the net energy that comes out from all of the reactions is more than the energy that we put in. But when we reach that equivalency, so if we make just enough energy from from all of the fusion reactions that it equals the input energy, that's called break-even. That's where the energy from fusion is equal to the input energy. And that's what the National Ignition Facility accomplished for the first time on Earth in a controlled manner a few months ago, earlier this year. They actually made a little bit more energy than they put in. So that's really exciting. For a fusion power plant, we need actually significantly more. And that's what the fusion community is working on. We're trying to get that efficiency up. We want to get the energy out to be way more than the input energy. And the reason we're working so hard on that is that fusion promises to be a safe, clean, abundant source of electricity. There's no greenhouse gases released in that reaction. There's no chance of a meltdown, which is the primary risk of nuclear fission power plant, which is the current nuclear technology available today. There's also no long-lived nuclear waste that we have to deal with. And fusion can act as a reliable baseload power output for electricity generation. Basically, fusion doesn't depend on the weather to create output. Now, this is not to say that fusion is not without its drawbacks or problems. The biggest one, I think, is that making electricity from a fusion power plant is not feasible at this point. Again, we're still working to get that efficiency up. I want to change gears a little bit and talk about the fuel that fusion power plants are going to use. They're going to use a state of matter called plasma. It's often called the fourth state of matter. And it's a state of matter where the electrons have been stripped off of the nuclei, and and those particles kind of exist in a soup together. We've got the positively charged atomic nuclei, we call them ions, floating around with those negatively charged electrons. And plasmas are all around us. Lightning is a plasma. Here's an example of a plasma ball, which is a nice example of a cool or a warm plasma. And as I indicated, we use plasmas in a lot of our fusion experiments, and power plants will use plasmas as well. This example is from a fusion experiment that is lives in the UK. In a fusion power plant, those plasmas have to be really, really hot and really, really dense, which means we have to keep those particles tightly confined. We have to keep them close to each other, and we have to keep them hot. And there's a couple of different ways to do that, and I want to just introduce a couple of them. And the first example I want to start off with is kind of the archetypal example of a fusion power plant. It's the sun. The sun is driven by fusion. But it's this big, massive object, and its own gravitational attraction confines the particles, and it can actually accelerate those particles enough to fuse. And so it's an example of gravitational confinement. The second example is the National Ignition Facility, which is an example of inertial confinement. Inertial confinement typically uses some type of shock wave to compress the fusion fuel. And the National Ignition Facility uses lasers to set up that shock wave. So here's a little cartoon diagram of one of their experiments. The blue lines are lasers, and they come in and they hit a gold cylinder. It may be hard to see, but there's a gold cylinder here that the lasers hit. And once they hit that gold cylinder, this sets up a nice uniform shock wave that propagates inward and compresses the fusion fuel, which is the white ball in the center here. And the last example comes from magnetic confinement fusion. And it's an experiment called ITER, which is currently being built in the south of France. It's a little diagram of what ITER is going to look like with a cutaway. This pinkish purple stuff is the plasma, and it's a little bit hard to see, but it's going to live in a donut shape. It has a donut shape, and in ITER it's going to use a magnetic field to confine the particles, which are then going to be heated enough to the point where they can fuse. My background is in magnetic confinement fusion, and all of the examples that I show come from magnetic confinement fusion. So I just want to go over a little bit more of the things that we care about in magnetic confinement fusion. And the first thing I want to talk about is why we use magnetic fields in the first place. And the short answer is that we use magnetic fields to protect the walls from melting. So I mentioned that these plasmas have to be hot. They actually have to be insanely hot, something like 100 million degrees, which is roughly 10 times hotter than the core of the sun, in order to fuse. And as you can imagine, those kinds of temperatures are going to melt any wall material. So the idea is to use magnetic fields to keep the particles away from the wall. And if we go over to our little diagram over here, I'll kind of talk about what that looks like. This purple surface here represents kind of the edge of the hottest part of the plasma. It's also the edge of the containing magnetic field. So everything on the inside is super hot and confined to inside the purple surface. And this purple surface has a gap. We want to keep it reasonably far away from this wall. And then we have ways to cool down the plasma as it approaches the wall. This works because ions and electrons follow magnetic fields. A lot of times we'll use a donut or a torus shape so that there's no end to the magnetic field. The plasma just exists in a never-ending loop of magnetic field. But these torus-shaped magnetically confined plasmas are highly dynamic systems. So again, I want to direct your attention to the figure where we see some camera shots of a plasma evolving over the course of 3 seconds. Now, what we can't see are a bunch of the other dynamics. There's dynamics that are too fast for us to visually see. They can be, microseconds or even shorter. And there's dynamics, again, that are too physically small on microscopic scales to see in a picture like this. But understanding all of the dynamics, the really fast ones and the slower ones, is key for steady state operation of a power plant. We want a power plant to operate for months or years without stopping. So we spend a lot of effort studying these dynamics. So we use, just another bit of vocabulary, we use diagnostics, which is just an instrument to study the plasma. So later on, I'll talk about diagnostics. That's just, an instrument we use for these studies. But it's really hard to, diagnostic access to these plasmas is limited because they're so hot and so dense. We can't put a thermometer in the plasma, it would just get obliterated, right? So we have to make these measurements a different way. And even the diagnostics that we do use eventually are going to see wear and damage from this harsh environment, right? And this brings me to my first example, which doubles as an example of how I used Python in my analysis of fusion data. So this is an example of, this is a project that I worked on. It's also a way of overcoming some of those diagnostic limitations. And the idea is that we take information from multiple diagnostics, we combine it to get a single unified estimate for a given plasma characteristic, for example, the temperature, right? And this process, this clever analysis routine can reduce the need for maintenance or replacement of parts on the diagnostics. Even as their performance degrades, we can maintain a reasonable amount of accuracy. It also enables the measurement of some plasma characteristics that you can't measure using a single diagnostic. So you take little bits of information from multiple diagnostics to get an estimate for a plasma characteristic that otherwise you wouldn't be able to measure ever. Right? And that's the project that I worked on. And I'm happy to talk at length about what exactly I did, but I'm just going to say that I was able to measure something that's really, really hard to measure, and that improved measurement led to a better estimate of the global energy efficiency of our experiment. And of course, this knowing what the efficiency is a key metric for fusion performance, right? So this was a really nice result for the group. And as I indicated, I use Python as my primary tool. I'm not going to show any Python code, but I thought it might be useful to illustrate my workflow because I think it helps illustrate why Python was such a great tool for this project. So the workflow was, I used data from one diagnostic. I combined it with results from a model of that diagnostic. And those two combined to get a probability distribution of that diagnostic, which then went into a Markov chain Monte Carlo routine for parameter estimation. And then I did the same thing for my second diagnostic and my third diagnostic, et cetera. Again, Python is a really great tool for this. I was able to take advantage of the rapid modular development environment. I was able to focus on that the workflow for that first diagnostic and start getting results in the MCMC loop, albeit less accurate, while I was working on the workflow for the second diagnostic. And once that was complete, I could wrap those two together very easily. It also allows for modular execution. So if data is not available for some reason, I can just exclude that module from the analysis. And of course, this is all enabled by the extensive set of scientific computing packages: NumPy, SciPy, MCMC samplers, data visualizers. You get the point. And a lot of those exist because of the large and active development community, because of you guys. Right? So thank you. I did run into some limitations in my analysis, mainly in the form of speed or efficiency. I ended up using some pre-calculated tables to speed things up. I know there's a lot of other ways to do computational acceleration, but those are those are some places where I ran into a bottleneck. I also had to integrate with some other languages, and I found it to be cumbersome. Not impossible, but it was a little bit cumbersome. There's always this issue of serialization and deserialization when you're trying to communicate between different languages. Nevertheless, Python is Python is a great tool. It was a great tool for this project. And it's a standard tool for the Fusion community. I'm not the only person who uses Python. A lot of people use Python as their standard analysis language. Furthermore, integrated techniques like this are becoming the standard in Fusion. And so, ways that you can get involved are, anything that involves scientific computing packages, that's going to help the Fusion community, and data aggregation. So flexible modules for combining data, ways to accelerate computation, and then I've identified efficient MCMC samplers as just a specific example of where I encountered some bottlenecks in my own routine. But, development of these scientific computing packages for the Python community at large is going to help the Fusion community. And I guess I do want to kind of go back to this flexible modules for data, combining data, kind of leads into the second example, which is how do we handle large amounts of Fusion data? And for this specific example, I want to go into a little bit more detail on ITER. I'm going to call out ITER for this example. ITER is a global collaboration. And so here's a picture of ITER. It's another cross-section. Again, this pinkish purple stuff is the plasma. And down here, kind of in orange, I hope you can see it, is a person for scale. ITER is going to be huge. It's going to be the largest device of its kind once it's complete. And it has two main goals. We want it to make more energy from fusion than they put in. So they want to do break even plus a little bit more. and they want to learn the necessary physics to design a prototype power plant that can actually put electricity on the grid. But because it's a global collaboration, data has to be available across the globe, often in real time. There's going to be control centers in different places around the world that all have to have access to the experimental data as an experiment is running. So this is a global problem, and at its peak, they estimate that ITER is going to generate roughly 2 petabytes of data per day. And I was looking up some stuff. I think it pales in comparison to how much data is uploaded to YouTube every day, but it's about half of what is uploaded to Facebook every day. So it's a lot of data. Maybe it's not a lot of data for some of you. It's definitely a lot of data for us. We have not been in this situation before. And so, you know, any expertise in big data is going to help. And I do kind of want to, zoom in a little bit more and talk about, and give it a little example of how they want to make the data accessible, not in real time, but for analysis. And so some really smart people sat down and thought about a platform for making a unified access point for all of the data. They call it the Integrated Modeling and Analysis Suite for ITER. And it's designed to streamline and unify access to data, analysis routines, and even results from simulation for all users around the world. And they want, regardless of what language they program in or what data format they prefer to use, they want it to be a fairly uniform experience for all of the users. And they decided to use an interface data structure. This can be data from storage, results from simulation, results from another module, etc. And that goes into an access layer that does a lot of interfacing and interpretation. And then you can run your code or maybe start a simulation. Once that's done, it goes to another access layer and then out to the world. And I think they tried to create something that's uniform like this to combat the siloing that has kind of grown up, becoming just kind of standard in the Fusion community, where groups will continually reinvent the wheel and remake analysis that does similar things. So they're trying to combat that, make a uniform platform, while still recognizing that a lot of groups out there have made some really nice analysis codes and tools that can be shared, but maybe it's not in a language that another group is familiar with. So they're really trying to share resources here. I guess to finish up this example, I want to emphasize that, like a lot of industries today, Fusion is generating and collecting a lot of data, right? And so all of those solutions that companies have come up with for data management are relevant to Fusion, and we can use that expertise. This is something that is new for us, right? And I just want to point out that all Fusion power companies will be making significant amounts of data, and they're going to need to move it, combine it, analyze it, just deal with it, even if they're not a global collaboration. So ITER is a specific example, but any approach to Fusion is going to be making significant amounts of data. And so again, I've highlighted a couple of places, specific places where I see, Python experts being able to contribute. There may be others. This is not designed to be an exhaustive list, rather more like some ideas. Now, moving on to the last example, it's a little bit different. It's not as data-centric. It's an example of an application of machine learning for control of fusion devices. And to start off, I kind of want to remind you way back at the beginning of the talk, I said that these plasmas are really dynamic systems, right? And sometimes the dynamics that are going on can turn into instabilities. And some of those instabilities can become catastrophically unstable such that we lose the plasma. That's called a disruption. And it's an uncontrolled loss of plasma. So you have these super, super hot particles that all get ejected to the wall in an uncontrolled way. And here I've got an example of that happening in an experiment. So here in the center, we've got a relatively quiescent plasma, and then it disrupts. And here's a picture that was taken right during the disruption, and you can see there's a very strong wall interaction. That's where all of these particles are slamming into the wall. And then this last picture over on the right it shows the damage to the wall that occurred because of that disruption. You can see it's kind of melted here. And as we push to hotter and hotter plasmas and higher densities in those plasmas, it becomes more and more likely that the damage to the machine is going to be significant. And a power plant grade plasma is very likely to be significantly damaged if it ever disrupts. But fortunately, we have ways to prevent disruptions as long as we can predict them. So this idea of predicting disruptions in advance has been an area of research for a decade. And it's a great application for machine learning. It's a hugely multi-parameter problem. And again, people have been working on this for a decade. And at this point, they are largely successful. They have high accuracy at predicting disruptions. And I just want to talk about this figure. What it is, this is an ROC curve from a recent paper. And you've got your true positive rate on the vertical axis versus your false positive rate. They're trying to do predictions. And if you look at the 5%, excuse me, false positive rate, they're up around 90% true positive rate. And that's pretty good. I think with a little bit more, they want to be maybe up around 95% true positive rate. But this was a new technique. So, but I do want to point out that for all of these great results, the test data comes from the same machine as the training set. So the training set and the test data all come from the same machine. And you might say, well, why would I ever want to do anything different? That's the way machine learning works. Well, remember I said that we don't, high power disruptions are very likely to be damaging. So we want to use training sets from smaller, cheaper devices and try to deploy it on larger machines. So we want to use, so we've got just a little picture showing some relative scales of devices here. Here we've got a machine called TCV, and it's kind of relatively small. In the center, we've got a machine called JET, and JET is the largest experiment that is currently taking data in the world right now of its type. And then we've got ITER kind of for scale. ITER will be the largest device of its type once it's built. So the idea is that we want to take data from, say, a bunch of machines that are TCV sized and try and train a set and then deploy that on JET. for example, because JET has actual data. And consistently, time and again, it doesn't matter what type of algorithm you use for your machine learning, time and again, the research shows that we need a few disruptions from the larger machine to accurately predict disruptions on that machine. And this is a this is a well-known limitation of machine learning. It's very difficult for machine learning algorithms to extrapolate outside the parameters in their training set. But this is an area of active research. We don't have a solution for it yet. But we're working on, figuring that out. And I just want to finish up this example by taking it out just a little bit more generally. And machine learning is being used for a lot of feedback and control of all fusion devices. It's also being used in analysis. And I just want to make the point that all fusion devices need some type of feedback and control. They don't all have disruptions, but they're all going to need a control system. And, contributing to, new machine learning techniques is a great way to get involved, or, flexible feedback and control modules. Again, a great way to get involved. And kind of going back to that specific example, if there's a way to have a machine learning technique that can reliably extrapolate beyond the parameters in its training set, that would be a game changer for fusion, right? It's a very difficult thing to do, but that would be a game changer, and really would be amazing, frankly. Let's see. I just want to, finish up by re-emphasizing that fusion power is, it's a growing industry, and we have increasing needs for software engineers and developers. I showed 3 specific examples, but they were designed to illustrate typical challenges facing the fusion community, regardless of the approach to fusion power. And hopefully over the course of this talk, I convinced you that there are places where you can contribute. Your area of expertise better than I ever will, right? And hopefully I encourage you to think, hey, how might I address the machine learning problem, or how might I solve data management of petabytes of data per day, right? How are you going to help us light this bulb up? And hopefully I've encouraged some of you to actually get involved in the fusion community. And if that sounds interesting to you, I encourage you to look up these resources. The Fusion Industry Association has a group of startups specifically who are trying to bring fusion to the grid. There's also a group of companies that are helping them to bring fusion to the grid. So I encourage you to check that out. I also encourage you to check out usfusionenergy.org, where you can stay up to date on news and trends in fusion. And I just kind of want to end with the note that there's a lot of companies, a lot of these startups are looking to hire Python experts specifically, and have no expectation that you know the details of the fusion science. And with that, I'd like to finish up and thank you for your attention.
Thank you, Lisa. 2.2 petabytes of data per day And I'm just thinking about that, you think about like Facebook or you mentioned those kind of comparisons to the other social medias and then the amount of data they're generating. But that's like kids' photos and like, there's just odd movies and this is like very targeted, data coming off of all these like sensors and all the interactions going in that experiment. So it feels very different than just social media data. 2.2 petabytes of important data is going into this system.
Yeah, that's
So that's awesome. Huge round of applause. Thank you so much for being with us here at Python Web Conference and kicking off the keynotes for day 4. That was just fascinating watching and looking at all the kind of ins and outs of like fusion and what you all are doing and just the day-to-day so I have a question, like, do you run these experiments? Is a fusion reactor like running constantly? Are you running these experiments constantly, or are there like special days when you're like, we're gonna fire it up and like hopefully it don't melt the world?
That's a great question. So it depends on the type of fusion experiment. So for the National Ignition Facility, they run maybe one, I think, per day, on the order of one per day. It's maybe between 1 and 3. I don't remember what the rate is. For some magnetic confinement experiments, they'll do a series of shots. So plasma experiment, a given plasma experiment might last between 100 milliseconds to like 5 minutes is what we're typically doing right now. And you can get a few of those in a day, so you'll have a run day. And the experiment that I worked on ran usually 5 days a week. And we would get roughly 100 shots. That's what we called them.
Yeah.
But those are individual things. Other ones they'll have like a campaign, and so they'll run every day for 16 weeks or something.
Yeah, and I just imagine like with the shot, the immense amount of data that happens in that such a shorter time period. So cool. Very cool. Well, folks, if you want to actually like talk to Lisa and ask Lisa questions more about this process or just say how cool this is, we can all jump over into the face-to-face room. Laura will post that over into the Slack channel, and we'll make sure Lisa gets over there as well to answer any of your questions. And thank you again so much for being with us. Huge round of applause to you, and just wow. There's lots of opportunity, it sounds like, given this new technology.